Hi guys, and welcome back to my channel. This is the first kind of episode. It's a roundup of the tectonic processes and hazards series. I've gone through the whole specification already on my channel. I'll link the playlist up here if you haven't seen it. But this is just going to be compiled into one video. It might be like 40-50 minutes long, but it should give you the detailed notes that you need for your exam. I'm also going to do the essentials, so if you've only got 10-15 minutes to cram everything in, that'll be a really good video for that. But today is going to be the detailed notes of what you need to know for your exam, just in a much more concise way than the rest of the videos in this series. So stick around if that's what you think might be useful. Let's get straight on into this. The global distribution of hazards. A hazard is a potential threat to human life and property. A natural hazard can be either hydrometeorological, caused by climate processes, or geophysical, caused by land processes. Geophysical hazards occur near plate boundaries. These plates move at different speeds and directions, which cause collisions, earthquakes and volcanic activity. Earthquakes can also occur near the middle of plates, called intraplate. The causes of these are not fully understood, but it is assumed that plates have pre-existing weaknesses which become reactivated, forming seismic waves. For example, an intraplate earthquake may occur if a solid crust, which has weakened over time, cracks under pressure. Volcanic hotspots, such as the Ring of Fire, are also situated along the centre of plates. This is a localised area of the lithosphere, the Earth's crust and upper mantle, which has an unusually high temperature due to the upwelling of hot molten magma material from the core, first theorised by Tuzo-Wilson in 1963. At hotspots such as the Hawaii hotspot, magma rises as a plume. Usually the most powerful earthquakes occur at convergent or conservative plate boundaries. Tectonic trends since 1960. The total number of recorded hazards has increased. The number of fatalities has decreased, but there are some spikes during mega disasters. The total number of people being affected by tectonic hazards is increasing due to population growth. The economic costs associated with hazards and disasters has increased significantly. This is partly due to the development of infrastructure in more developed countries, costing more to repair. Also, increasing number of insurance policies, especially in developed countries, heightens the costs. Reporting disaster impact is very difficult and controversial for several reasons. It depends on whether you look at the direct deaths, so killed by the disaster straight away, or indirectly, by looking at how many people died of diseases that spread after the disaster. Some impacts take more time to become apparent. The location is important, as rural and isolated areas are hard to reach, so it may be harder to collect data from that area. Similarly, data may be difficult to collect in areas with very high population densities. Different methods may be used by different organisations. So as a result, different sources may quote different numbers of deaths and injuries. The number of deaths quoted by a government can be subject to bias. For example, during the 2004 Indian Ocean tsunami, the Burmese government claimed there were 0 deaths in Burma. This may be to show that the government was doing a good job in terms of aid and protection. Characteristics of the Earth's structure. The Earth consists of 4 sections. Firstly, the crust, also known as the lithosphere. This is the uppermost layer of the Earth, which is thinnest, least dense and lightest. Oceanic crust is only 7 kilometres thick, whereas continental crust can be up to 70 kilometres thick. Secondly, the mantle, also known as the asthenosphere. This is largely compiled of silicate rocks rich in iron and magnesium. The mantle is semi-molten, and a temperature gradient towards the core generates convection currents. This causes the circulation of the mantle and may contribute to the lithosphere's plate tectonic movement. The mantle is at a depth from 700 kilometres to 2,890 kilometres below the crust. Thirdly, the outer core. Dense, semi-molten rocks containing iron and nickel alloys at a depth of 2,890 kilometres down to 5,150 kilometres below the Earth's surface. And then fourthly, the inner core. This has a similar composition to the outer core. It's over 1,150 kilometres below the Earth's crust. The inner core is solid due to extreme pressures it experiences. The core's high temperature is a result of primordial heat left over from the Earth's formation and radiogenic heat produced from radioactive decay. Different plate boundaries. At plate boundaries, different plates can move either towards each other at destructive plate margins, away from each other at constructive plate margins, or parallel to each other at conservative plate margins. Different landforms are created at different locations due to different interactions. Plate boundaries. Divergent plate boundaries. Okay, so when continental and oceanic meet. The denser oceanic plate subducts below the continental. The plate subducting leaves a deep ocean trench. The oceanic crust is melted as it subducts into the asthenosphere. The extra magma created causes pressure to build up. Pressurized magma forces its way up through weak areas in the continental plate. Explosive, high-pressure volcanoes erupt through the continental plate, known as composite volcanoes. Fold mountains occur when sediment is pushed up during subduction, when oceanic and oceanic plates meet. The heavier plate subducts, leaving an ocean trench. Fold mountains will also occur. Built-up pressure causes underwater volcanoes bursting through the oceanic plate. As lava cools, it creates new land called island arcs. And when continental meets continental. Both plates are not as dense as oceanic, so a lot of pressure builds up. Ancient oceanic crust is subducted slightly, but there is no subduction of continental crust. Pile-up of continental crust on top of the lithosphere due to pressure between plates, and fold mountains are formed from these piles of continental crust. Constructive plate boundaries. When oceanic meets oceanic. Magma rises between the gap left by the two plates separating, forming new land when it cools. Less explosive underwater volcanoes form as magma rises. New land forming the ocean floor, left by lava filling the gaps, is known as seafloor spreading, as the floor gets wider. There is sufficient evidence to prove plate movement and seafloor spreading, theorised by Harry Hess in the 1940s. This provides some of the proof. Paleomagnetism is the study of rocks that show the magnetic fields of the Earth. As a new rock is formed and cools, the magnetic grains within the rock align with the magnetic poles of the Earth. Our poles, north and south, switch periodically. Each time these switch, the new rocks being formed at plate boundaries align in the opposite direction to the older rock. On the ocean floor, either side of constructive plate boundaries, geologists observe that there are symmetrical bands of rock with alternating magnetic polarity. This is the evidence for seafloor spreading. Continental and continental constructive margin. Any land in the middle of the separation is forced apart, causing a rift valley. Volcanoes form where the magma rises. Eventually, the gap will most likely fill with water and separate completely from the main island. The lifted area of rocks are known as horsts, where the valley itself is known as a graben. There are further forces influencing how convergent boundaries occur. Firstly, ridge push. The slope created when plates move apart has gravity acting upon it. It has a higher elevation. Gravity pushes the plates further away, widening the gap. As this movement is influenced by gravity, it is known as gravitational sliding. And then secondly, slab pull. When a plate subducts, the plate sinking into the mantle pulls the rest of the plate with it, causing further subduction. Conservative plate boundaries. Between any crust, the parallel plates move in different directions or at different speeds. No plates are created or destroyed, so no landforms are created. When these plates move, a lot of pressure is built up. On oceanic crust, this movement can displace a lot of water. On continental crust, fault lines can occur where the ground is cracked by the movement. Plate movements. There are two different types of crust, and they consist of different rocks. Oceanic, this consists of low density rock, mainly basalt, thin and newly created, whereas continental is a high density of rock, mainly granite, and it is thicker and older. The density of the plate will determine whether a plate subducts or is forced upwards. This will determine the landscape and the hazard the margin is vulnerable to. There are different mechanisms that could cause plate movement. Firstly, mantle convection. Radioactive elements in the core of the Earth's decay, which produce a lot of thermal energy. This causes the lower mantle to heat up and rise. As the magma rises, it cools down and becomes more dense and begins to sink back down towards the core. These convection currents push the plates. Secondly, slab pull. Old oceanic crust, which is the most dense plate, will submerge into the mantle. This pulling action drags the rest of the plate with it. It is important to note that tectonic movement isn't fully understood. Previously, convection currents were thought to be the primary cause of plate movement. However, researchers now believe slab pull is the primary mechanism of plate movement. Convection currents seem too weak to move massively dense plates. Earthquakes. Plates do not fit perfectly together, meaning they do not move in fluid motions. At all boundaries, plates can become stuck due to the friction between plates. You can try this by moving one palm of your hand against the other, and it's clear that at some points more friction between irregularities and bumps causing your hands to become slightly stuck. When the plates are stuck, the convection currents in the asthenosphere continue to push, which builds up pressure. It builds up so much that it cannot be sustained and the plates eventually give way. All of this pressure is released in a sudden movement, causing a jolting motion in the plates. This jolt is responsible for seismic movement spreading throughout the ground in the form of seismic waves or shock waves. The focus or hypocenter is the point underground where the earthquake originates from. The epicenter is the center above ground that is directly above the focus. Let's talk about the different kinds of seismic waves. You've got primary waves, which travels through solids, is compressional. It vibrates in the direction of travel and travels at about 4 to 8 kilometers a second. Secondary waves. These vibrate at right angles to the direction of travel. And it only travels through solid rocks and travels at 2.5 to 4 kilometers an hour. So a lot slower than primary waves. Love waves. These are near to the ground surface. A rolling motion producing vertical ground movement, travelling at between 2 and 6 kilometers an hour. And Rayleigh waves. These are vertical and horizontal displacements, travelling at 1 to 5 kilometers an hour, and it is compressional. Secondary and love waves are the most destructive as they have large amplitudes due to their different speeds. These waves will hit different locations at different times. The aftershocks that survivors feel are these types of waves arriving after each other. Intensity of waves will decrease further from the epicenter, as waves lose energy as they travel. However, this does not mean that the impacts felt or damaged will always decrease further from the epicenter, as other factors will affect a location's vulnerability, such as geology, geographic location, education of locals, durability of buildings, and mitigation strategies. The secondary hazards of earthquakes. Soil liquefaction. This affects poorly compacted sand and silt, where water moisture within the soil separates from the soil particles and rises to the surface. This can cause the soil to behave like a liquid, which can cause building subsidence or landslides. The shaking caused by earthquakes can weaken or damage cliff faces, hills, and snow material. Unconsolidated material or loose rocks can collapse. Landslides can travel several miles and accumulate material on the way. Risk varies with topography, rainfall, soil, and land use. Tsunamis. When an oceanic crust is jolted during an earthquake, all of the water above this plate is displaced, normally upwards. This water is then pulled back down due to gravity. The energy is transferred into the water and travels like a wave. The water travels fast but with a low amplitude. As it gets close to the coast, the sea level decreases, so there is a friction between the seabed and the waves. This causes the waves to slow down and gain height, creating a wall of water that is on average 10 feet high, but can reach 100 feet. Tsunamis are generated in subduction zones at convergent plate margins. Most tsunamis are found along the Pacific Ring of Fire, hence the most vulnerable countries are likely to often be located in Asia or Oceania. The impact of tsunami depends on various human and physical factors. Population density of an area hit. If the population density is higher, there are more people likely to be affected. Coastal defences, the duration of the event, wave amplitude and distance travelled, the gradient of the continental shelf, the shape of the land, as bays will funnel and concentrate tsunami waves, warning and evacuation systems, and the level of economic and human development. Volcanoes. Primary hazards caused from the volcano tend to have fast speeds of onset. Lava flows. Streams of lava that have erupted onto the Earth's surface. Fast flowing lava can be very dangerous, which depends on the lava's viscosity. Pyroclastic flows. This is a mixture of hot, dense rock, lava, ash and gases, which move very quickly along the surface of the Earth. Due to their high speeds, pyroclastic flows are extremely dangerous and can cause asphyxiation for anyone unfortunate enough to be caught by the flow. Tephra and ash flows. When pieces of volcanic rock and ash are blasted into the air, this can cause serious damage to buildings, which can collapse under the weight of ash or tephra. And volcanic gases. When pieces of volcanic rock and ash are blasted into the air, are released into the atmosphere. Due to their potency, volcanic gases can travel long distances. Secondary hazards occur as a result of heat produced by a volcano. Lahars, a combination of rock, mud and water, which travel quickly down the sides of volcanoes. These occur when the heat of the eruption causes snow and ice to melt, or alternatively, when an eruption coincides with heavy rainfall. A Yerkalop. Snow and ice in glaciers melt after an eruption, which causes sudden floods that are very dangerous. Acid rain, caused when gases such as sulfur dioxide are released into the atmosphere. Classification and theories of tectonic events. A disaster, a serious disruption of the functioning of a community or society involving human, materials, economic and environmental losses, which exceeds the ability of the affected community or society to cope using its own resources. The risk a community faces from a natural hazard can be calculated with this equation. How developed a country is significantly affect how resilient the population is and their capacity to cope with a hazard. A place may be high risk if their capacity to cope is low, they are quite vulnerable, or the model is high or has large intensity. Degg's model. Hazards should not be confused with natural disasters. A disaster will only occur when a vulnerable population is exposed to a hazard. Degg's model is a good representation of this concept. If the population is not vulnerable, the hazard will not have a significant effect, thus the event will not be disastrous. Different organisations will define a hazard and disaster differently based on their interests and what they believe to be most important. For example, the United Nations Office for Disaster Risk Reduction define a disaster as a serious disruption of the functioning of a community or society involving widespread losses and impacts, which exceeds the ability of the affected community or society to cope with using their own resources. There are other ways to classify a tectonic hazard, each measure having different successes and downfalls in correctly representing the magnitude and implications of a disaster. The volume of people affected. The International Disaster Database classifies a disaster as an event where more than 100 people are affected or more than 10 people die. The economic cost of a disaster. Jobs lost, cost of repairs needed, economic productivity loss. The UN Sendai Framework is an initiative to reduce economic losses due to a disaster, after huge economic losses during the 2011 Tokyo earthquake and tsunami. You can compare a tectonic disaster to previous events, prediction models, or average statistics for that location. Some events may be more severe than the average tectonic hazard due to a series of factors coinciding, such as bad weather and recent deforestation, will increase the tsunami travelling inward. It is important to treat statistics carefully. Rare mega disasters could skew the statistics. The Park model. The Park model is a geographical representation of human responses to hazards. The model shows the steps carried out in the recovery of a hazard, after giving a rough indication of time frame. The steepness of the curve shows how quickly an area deteriorates and recovers. The depth of the curve shows the scale of the disaster. Stage 1, relief, hours or just days. This is the immediate response, medical aid, search and rescue, and the immediate appeal for foreign aid and the beginnings of global responses. Secondly, rehabilitation. This is from days to weeks. Services begin to be restored. Temporary shelters and hospitals are set up. Food and water is distributed and coordinated foreign aid such as peacekeeping forces. Stage 3, reconciliation. This is from weeks to years later. Restoring the area to the same or better quality of life. Area back to normal. Ecosystem restored. crops are regrown, infrastructure is rebuilt, and mitigation efforts for future events. The model also works with a control line to compare hazards. An extremely catastrophic hazard would have a steeper curve than the average and have a slower recovery time than the average. The pressure and release model. The pressure and release model is used to analyse factors which cause a population to be vulnerable to a hazard. On one side of the model, you have the natural hazard itself, and on the other side are different factors which have increased a population's vulnerability to the hazard. The vulnerability is often rooted in social processes. These are dynamic and are ever-changing and are often unrelated to the hazard itself, such as poverty or poor governance. The PAR model is complex. No two hazards are the same, and the factors leading to vulnerability are interconnected and hard to measure. If we reduce the social factors affecting a population, we can reduce the pressure that they face, and so reduce their vulnerability to the effects of natural hazards. The progression of vulnerability is split into 3 sections. The root causes are often caused by economic, demographic, and/or political processes, often affecting large populations or entire countries. Dynamic pressures are local, economic, or political factors that can affect community or organisation, and unsafe conditions are the physical conditions that affect the individual. Therefore, the number of people affected will increase the closer the factor is to the root cause. Vulnerability can also be defined differently, depending on who or what is affected. Physical vulnerability is the individuals that live in a hazard-prone area, with little protection naturally or through mitigation. Economic vulnerability. People risk losing employment, wealth or assets during a hazard. MEDCs, more economically developed countries, tend to be more economically vulnerable than LEDCs, the less economically developed countries. Social vulnerability. Communities tend to be unable to support their disadvantaged or most vulnerable, leaving them at risk to hazards. Knowledge vulnerability. Individuals lack training or warning to know the risks of a hazard or how to safely evacuate. Alternatively, religion and beliefs may limit their understanding of hazards. Hazards are an act of God, so individuals don't mitigate or evacuate, known as a fatalist belief. Environmental vulnerability. A community's risk to a hazard is increased due to high population density in an area. The pressure release model suggests that a variety of factors lead to a population's vulnerability. Common factors that affect the vulnerability of a society. Root causes such as weak governance, mismanagement by industry, NGOs or IGOs, and a high reliance on products easily affected by hazards such as local agriculture or imports by air during a volcanic eruption. Dynamic pressures, the second part. The lack of training or knowledge in local people, rapid urbanisation, poor communication between government and local people, and the natural environment. And then unsafe living conditions, lack of infrastructure, clean water, sewage removal and electricity. Dangerous location of settlements, close to nuclear stations or to the natural hazard itself, and no warning systems for locals. Tectonic hazard profiles. A hazard profile compares the physical characteristics which all hazards share. Hazard profiles can help decision makers when deciding where to allocate the most human and financial resources. It is easy to measure a single hazard like earthquakes, but it's much more difficult to manage multiple hazards or events, where secondary hazards are much more destructive than the actual hazard itself. The characteristics of a hazard profile include frequency, magnitude, duration, speed of onset, fatalities, economic losses, and spatial predictability. Evaluating the effectiveness of models. Hazard models are useful, but the unpredictability of hazards make the models less effective at accurately representing human responses to hazards. It may be useful to ask some questions when evaluating how effective these models are. Can they be applied to every hazard? Some hazards are more complicated and require a more complex model. It may be useful to apply each of these to case studies to see how they compare. Does the model take any aspects of the hazard into account, such as level of development? Is there any time frame? Do the models accurately lay out the time taken for a full response, and how this changes due to aspects of the hazard, such as intensity? And could the model be less vague or include more steps that can be applied to all hazards? Does the model present hazards currently? Are there any alterations that could be made for the hazards affected by climate change? with a model eventually not represent human resources at the time. Measuring volcanic events. The Volcanic Explosivity Index, the VEI, measures the relative explosiveness of a volcanic eruption, based on the height of ejected material and a duration of the eruption. The scale goes from 0 to 8 and is logarithmic. The modified Mercalli scale measures the destructiveness of an earthquake. It is a relative scale, as people would feel different amounts of shaking in different places. It is subjective and is based upon if people wake up, if furniture moves, how much damage structure receives. The scale varies from I to XII. It's a Roman numeral scale. I is generally not felt or detected by seismographs, or XII, or 12, is a nearly total destruction. It doesn't consider economic, social and environmental impacts. The moment magnitude scale measures the amount of energy released in an earthquake, a scale from 0 to 9. It's a simple measure, so environmental or social impacts must be inferred. The Richter scale. This measures the amplitude of waves produced during an earthquake. It is the most widely used scale as it's absolute. It must infer social or environmental impacts, which can be misleading. The highest Richter scale earthquake readings won't necessarily be the worst disasters. Like the VEI scale, it is logarithmic. Managing tectonic hazards. Hazards can be responded to by preventing them directly, being prepared for the next hazard, mitigating the event, or completely adapting your lifestyle to limit that hazard's effects. Prevention. Volcanic eruptions cannot be prevented. The only risk to people cannot be prevented by not allowing people near volcanoes. Preparedness. Monitoring increases the notice of volcanic eruptions, meaning that warnings can be given to get out. Education on volcanoes in areas of risk, so people know what to do if there's a volcanic eruption. Planned procedures for evacuation and training response teams. Mitigation. Direct intervention to the volcano, such as concrete blocks to steer lava away from areas at risk. Strengthening buildings that are at risk of mud flows or ash pileup. Evacuation and exclusion zones, or mitigating effects on health by having emergency aid and rescue. Or adaptation. Move away from the area at risk. Capitalise on opportunities such as encouraging tourism, and change profession so it is less likely to be affected by volcanic hazards. The hazard management cycle. The hazard management cycle outlines the stages of responding to events, showing the same stages take place after every hazard. Preparedness, response, recovery and mitigation. Monitoring and prediction. It is not possible for us to predict accurately when an earthquake will happen. Instead, the risk of an earthquake can be forecast based on statistical likelihood. Forecasts can be based on data and evidence rather than gathered through global seismic monitoring networks and also from historical records. Scientists can sometimes predict volcanic eruptions with some degree of accuracy. Scientists can use special equipment to monitor volcanoes and detect signs of imminent eruption. Small earthquakes, called tremors, changes the top surface of the volcano as it swells when magma builds up. Changes to the tilt of the slope or angle when the magma builds up. Mitigation identifies the characteristics of the potential hazard and what can be done to reduce their impact on people, such as land use zoning, building codes and regulations, and protective defences such as the tsunami wall. Preparedness. Minimising loss of life and property. Developing preparation plans, developing warning systems, stockpiling medicines, food and water, etc., and education, training and drills. Response. Coping with a disaster. The main aim will be to rescue people and reduce economic losses through search and rescue efforts, evacuating people, restoring vital infrastructure like water and electricity, and restoring vital services like law enforcement and healthcare. Local aid and international aid focuses on short-term and long-term recovery. Short-term recovery, providing food, aid, water, shelter, financial assistance so that people can rebuild their livelihoods. And longer-term strategies such as rebuilding homes, building and repairing infrastructure, and reopening schools and businesses. Management approaches. There are 3 different approaches to managing tectonic hazards and reducing their impact. Modify the event, modify the vulnerability, or modify the loss. Modify the event first. We cannot control seismic activity. However, we can control the design of buildings, which can be said to be the biggest killer during a natural disaster, through civil engineering using micro and macro methods. Micro methods, strengthening individual buildings and structures, whereas macro methods are large-scale support and protective measures designed to protect whole communities. For earthquakes, these use mainly micro approaches, emphasis put into public buildings like hospitals, police stations and other vital infrastructure. Schools and factories are strengthened to help shelter people, and some improvements to private housing. For tsunamis, tsunami walls work for a given amplitude and threshold of wave, replanting coasts with mangroves and coastal forestry, which dissipates energy from waves. For volcanoes, diverting the flows of lava, reinforcing house roofs to withstand large deposits of ash. Types of modification: land use zoning, prevent building on low-lying areas of high risk. It is low cost, reduces vulnerability, however it stops economic development on some high-value land, and strict enforcement is required. Resistant buildings. Buildings with deep foundations, slope roofs so that ash doesn't build up and create pressure. This can help prevent collapsing and protects people and property. However, it is high cost for larger families. Low-income families can't afford this. Tsunami defences. Sea walls which stop waves travelling inland, reduces damage and provides security. However, it's very high cost, it doesn't really look nice and it cannot be overtopped. Lava diversion. Barriers and water cooling to divert and slow down lava flows. This diverts lava away and it's fairly low cost, but it only works for really low viscosity. Modify the vulnerability. High-tech scientific monitoring. These monitor volcano behaviours and predict eruptions, but it is only possible in some locations. And warning and evacuation systems can help to save lives, but it is costly in LEDCs and they're not properly monitored there, and it doesn't prevent property damage. Community preparedness and education. This is low cost and often implemented by NGOs, can save lives through small actions. But again, it doesn't prevent property damage, and it is harder to implement in isolated rural areas. And adaptation, moving out of harm's way and relocation. This helps to save lives and property, but high population densities prevent it, disrupts people's traditional home and traditions. Modify the loss. Short-term aid. Search and rescue and also food, water, aid and shelter can help to reduce death toll by saving lives and keeping people alive until long-term aid is provided. This is high cost and has technical difficulties in isolated areas. Emergency services are limited and are poorly equipped in LEDCs. Long-term aid. Reconstructions planned to rebuild an area and improve resilience. Reconstruction can help to improve resilience through land use planning and better construction methods, but they're very high costs. Needs are quickly forgotten by the media very shortly after a disaster. Insurance. Compensation to replace these losses. Allows people to recover economically for paying reconstruction, but it doesn't save any lives, and not many LEDCs have insurance. The role of communities. In remote and isolated areas, it may take a long time for aid to come, and people may begin local recovery operations. Communities may clear debris from roads and set up temporary shelters themselves. The role of NGOs and TNCs. NGOs play a very important role in providing funds, the coordination of rescue efforts, and helping to develop reconstruction plans. Occasionally, TNCs and NGOs may cooperate. Charity buckets or events may be organised by businesses to improve IGA's ability to help. Development and governance. Governments of developing countries may not prioritise investing money into hazard mitigation, as they tend to focus their resources on development and economic growth. This lack of investment in hazard management often means that less developed countries and their populations are more vulnerable to hazards. The risk-poverty nexus states that poverty is both a contributing factor and a consequence of a natural hazard. It also suggests that a positive feedback mechanism can cause further economic losses for already poor countries. Lower-income households and communities are generally more affected by impacts and losses. There are various types of inequality, each affecting a community's resilience to a hazard. Firstly, asset inequality, related to housing and securing income, purity of tenure, and also agricultural productivity. Political inequality, where certain groups of people, especially the wealthy and elite, hold a lot of power and political influence. Social status inequality. often directly linked to space and has a bearing on each other's dimensions of inequality, including the ability of individuals and groups to secure regular income and access services. Entitlement inequality. This refers to the unequal access of public services and welfare systems, as well as inequalities in the application rule of law. Hazard vulnerability. There are many factors that contribute to a population's vulnerability, such as unstable governance, corruption, population density, geographic isolation and accessibility, and levels of urbanisation. As in urban areas, these tend to be affected worse by hazards due to two factors. They're usually more densely populated and have larger amounts of infrastructure, meaning there is more economic damage. Governance. Meeting basic needs when food supply, water supply and health needs are met. The population is generally less vulnerable to secondary hazards such as diseases. Planning. Land use zoning can reduce risk by preventing people living in areas of high risk. Secondary hazards may be made worse by deforestation. Preparedness. Education and community preparedness programs raise awareness and teach people how to prepare, evacuate and act when a disaster strikes. Corruption. If government politicians accept bribes and do unethical things, then vulnerability would increase as money will be invested into crucial areas like emergency services. Tectonic megadisasters, the characteristics. These are large-scale disasters affecting large spatial areas of population or a large population. They pose problems in effective management and minimise the impacts. The scale of the impact may require international support and aid, however they are fairly low probability and fairly rare. The globalisation of production and supply chains has allowed international businesses to reduce the costs and become more efficient. However, mega disasters significantly damage global businesses. There are different examples of business disruption by mega disasters. The 2011 Tokyo earthquake and tsunami. There was a knock-on effect for TNCs such as Toyota or BMW, which operate and source products from Japan. This cost potential revenue for those TNCs and caused general economic uncertainty. And the 2011 Ijaki eruption. The significant ash cloud closed European airspace, which led to the halt of goods and trade into the EU by air. This resulted in Kenyan flowers to be imported to the EU, which couldn't be transported and wilted. And that is the end of this detailed, very detailed revision guide for the tectonic processes and hazards unit over here on my channel. Please do subscribe down below so that you don't miss all of the other ones. I'm also going to do just the essentials, just the basics for this topic as well. So it'll be even shorter than this one. I think this is about 40 minutes, so I'm hoping the next one will be less than 15. But yeah, subscribe down below so that you don't miss that, and I will see you soon.